Hello, I'm Mr. Sobolewski. For those of you that don't know me, if you happen to be watching from another class, in this video I'm going to go through what I'm going to consider part one of the essential chemistry skills. So this is unit one. It's what we've been working on for a few weeks now. I'll do a second video with a few more things coming up before our unit one test, which could be in a couple weeks. So these are the 8 things I'm going to go through. What I try to do in this video is keep like a little number up here. So you see 1, 2, and 3, and 4. So if you want to kind of skip ahead to the number you want to see, look up there in the corner for the numbers. All right, let's start right away with measurement. So you guys have been taking measurements your whole lives. It's really nothing new. We just want to make sure we take precise measurements in chemistry. So if I were to say, what is that line at? Well, naturally you would say, well, okay, so it's between 1 and 2. It's between 1, 2, 3, 4. So it's between 1.4 and 1.5. So something like 1.44. And if this were centimeters, we would add centimeters. I mean, this is something everyone knew how to do coming into class. So I don't want you to try to relearn how to do this. This is very basic. I just want to show you what you're doing when you make this measurement. You're recording everything you know, and you're recording one unknown digit. So you know it's between 1 and 2. You know it's between 1.4 and 1.5, so known, and then you're guessing 1. This last 4 is totally up to you. If you said 3, that's fine. If you said 2, if you said 5, that's all fine. So that's how we're going to take measurements in here. It just depends on the device you're using. So if I gave you another example, let's say I have this ruler now. Well, the difference is I took the little notches off, so now all you know is that it's between 1 and 2. And you're going to take your best guess at that, so 1.3. And again, centimeters if that's the unit. So your measurement depends on the device you're using. If your ruler looks like this, you're going to give me this extra digit of precision. If it looks like this, you're limited to the 1.3. And I always suggest, don't try to just memorize, if the digits are in the ones, I need 1 decimal. Just always look at the meter stick and use what you've always been using. Just use that intuition. It's a little more difficult if it falls on the line. So let's say you're trying to measure that point right there. Do you say 1? Do you say 1.0? Do you say 1.00? The trick I like to use is imagine if it fell off the line, what would you say? So with the same logic before, you might call that something like 0.5 or maybe 0.6. Or if it fell over here, you would call that maybe 1.5. These lines will tell you the precision you need. So if this one gives you a measurement to the 10th place, this one also needs to read to the 10th place. So you would call this 1.0. Another example, if it falls on that same line, right on the 1, but now we have these extra lines here, we're going to do the same thing. Let's imagine if it fell somewhere like right here. Well, this is going to be between 0 and 1. So I can start by writing 0 point. And 1, 2, 3, 4, 5. So it's between 0.5 and 0.6. So I can call that 0.55. This tells me that my reading has to go to the 100th place. So I'm going to call this 1.00. Okay? So that's how we take measurements. Let's move on. Number 2 is SI. SI is a System International, or the metric system. So we'll start with the base units. See if I can get this work. Your base unit of length is your meter. Your base unit of mass is the gram. Volume is the liter. Volume could also be meters cubed if you do like a length, width, and height. Temperature can either be degrees Celsius or Kelvin. Degrees Celsius is commonly used in the lab, but Kelvin is kind of a more absolute temperature. We'll get to that with gas laws. And the amount of substance, I put that in quotes because it doesn't really mean much now, but we'll be using this mole throughout the year. So it's just important to note that the amount of a substance really is the mole, and we'll explain that as we go through the year. SI prefixes. So this is also very important. So once again, these are your base units, but you're going to add prefixes before these to be more specific with the unit you're talking about. Which prefixes you have to memorize might depend on your specific chemistry teacher. I'll go with what I ask my students to memorize. I imagine it's going to be very similar. So I always start with just kind of what I call the unit here in the middle. This isn't really a prefix. That would be like your meter or your liter or your gram. If we want to go 10 times higher, that's deci. Which is sorry, I am wrong. That is deca, higher. Deca, which is dA. 10 times above that is hecto, which is H. And then kilo, which is K. Going below this, we have deci, which is lowercase d. Centi, which is cm. And milli, which is m. Okay, so these are your prefixes. These go in. Oh, I made another mistake there. Centi is just c. You commonly see centimeter. So once again, these are your basic prefixes. So every time we go up, that's 10 times, 10 times, 10 times. So therefore, to go from your regular unit to your kilo is 1,000 times. 1,000 meters in a kilometer, 1,000 grams in a kilogram. Let's keep going in the same way here. So that's 10, and that's 10. So, here we're going to have 1,000 times smaller for milli. Those are your basic 6. There are definitely a few more you need to know. Up here, I'm going to say mega, which is capital M. Mega means 1 million, or 10 to the 6th. So a megameter is 1,000,000 meters, megabyte, million bytes. And the difference here from kilo to mega is another 1,000 times. Okay? So therefore, to go from your unit all the way to your mega is 1,000 times another 1,000, so that's your million. Let's go down the other way. Down here is micro. And the symbol for that is the Greek letter mu, which looks almost like a U with a really long sort of stem on the front. Sometimes you also see it written like that. Micro is 1,000 times smaller than a millimeter. So therefore, if it's 1,000 times smaller than a millimeter, and a millimeter is 1,000 times smaller than your regular unit, so I realize I'm missing a line here. Yeah. It's going to be 1/1,000,000th for this. So a micrometer, which is commonly called a micron, is, I shouldn't even use my fingers, I can't get anywhere close to a micron, it'd be 1,000,000 times smaller. So 1/1,000,000th. 1 over 1,000,000. And the last one you should know is nano. Nano, lowercase n. Nano is 1,000 times smaller than a micro. Okay, so if we want to talk about how nano relates back to your original unit, it's 1,000 times 1,000 times yet another 1,000, so that is 1 billion. And since it's smaller, we'll say 1 billionth. Okay, there are other units, but these are the ones you'll see this year. I mean, if you go smaller than that, it's pico, and femto below that, but these are the ones that you should know. Significant figures. Okay, I thought I'd sort of introduce this by just talking about why we use sig figs as opposed to just kind of spitting a bunch of rules at you. So why sig figs are important. Let's say you have 2 lab partners and they each need to go record something. And one of your lab partners comes back and says, okay, it's 32 centimeters. The other one comes back and says, okay, it's 32.00 centimeters. Is there really a difference between these two? If you were in math class, you'd say no. Why waste the ink on writing those zeros? Because in math class, we deal with these theoretical numbers that are perfect. But in science, every number that you use in a problem, every number you use in a lab is a measurement. And measurements have to be used with proper precision like this. Okay? So there is a difference between these two numbers in chemistry, and that's why we use significant figures. Same thing if I said, how far is it from here to California? And someone says 3,000 miles. And someone else looks it up on Google and says it's 3,271.6 miles. Which one do you trust more? I would say you trust this one, because this is just kind of rounded off. It's sort of an estimate. So the number of significant figures, and by that we mean the numbers that are really important, the numbers that add to the precision, they definitely matter. This one, these are all significant. This one, only one of them is. So let's get to the rules now. First rule, all non-zeros are sig figs. If you're going to make a measurement and record a non-zero, it's going to count. 41, 2 sig figs. 497.2 is 4 sig figs. Okay. Next rule. All sandwiched zeros are sig figs. So if a zero just happens to be in the middle of one of these, it counts. Okay. So if you have 9,708, don't think because that's a zero it doesn't count. So that's going to be 4 sig figs. If you have something like 39.0084, sandwich zero. So 1, 2, 3, 4, 5, 6. Next rule of sig figs. Trailing zeros that are used to add precision to a decimal are sig figs. Trailing zeros, by those I mean any zeros at the very end of a number. So zeros at the end that are used to add precision to a decimal. So here's an example. 32.00. In math class, those zeros wouldn't matter, but here in chemistry, these zeros add precision. If you know for sure that those are zeros, you need to write them in, if that's your measurement. So this one would have 4 sig figs. Okay. If you have something like 0.263000, these zeros count. They matter. In math class they wouldn't, but here in chemistry they do. So 1, 2, 3, 4, 5, 6 sig figs. Next rule. Trailing zeros that are used to round off a large number, non-decimal, are not sig figs. So this is like where I said, if it's 3,000 miles to California, do these zeros count? And the answer is no. In chemistry, they're necessary. If you don't include them, all of a sudden your number changes. But you don't count those zeros as significant figures. They're just used to round off the number. They don't add anything to the precision. Okay? So trailing zeros are any zeros at the end of the number, as I said. In this one, they don't count, so this is 1 sig fig. If you have 90 milliliters, 1 sig fig. If you have 410 milliliters, that zero doesn't count, 2 sig figs, just those two. Leading zeros are not sig figs. Well, if trailing zeros are those at the end, leading zeros are anything in the front. So if you have 0.64, that zero doesn't count. That's also optional. You could just say 0.64. So that one's easy. 2 sig figs here. Usually this rule applies to long decimals like 0.0043. So this one, these zeros all don't count. They're necessary, yes. You can't not include them because the number would change by 1,000 times. But they don't add anything to the precision of the number. And with sig figs, we're talking about which numbers add to the precision, which are important for precision. And all these do is tell us where we're starting from. They're placeholders. So this one only has 2 sig figs. Another way you could look at this is if you were to put that number in scientific notation by kind of moving that decimal point 3 times to the right, you would just say 4.3 times 10 to the negative third. So you can see then it also has just the 2 sig figs. And just one more example, 0.00200. Well, now we're combining a couple of rules. Leading zeros never count. So those 3 are not significant. They're just placeholders. The 2 definitely counts. And these extra zeros here, let's check our rule. Are those zeros used to round off a large number? Definitely not. Are they used to add precision to a decimal? They definitely are, so those count. So this one is 3 sig figs. Last sig fig rule. A decimal intentionally placed at the end of a number indicates that all those digits are sig figs. This is just kind of a little formatting trick you might see and you might use too. Let's say you see 1,500 point meters. That point doesn't need to be there, and don't be tricked. It doesn't mean it's the end of a sentence or anything. If you see something written as 1,500 point, that point is intentionally thrown in there to show that all these are sig figs. So this would be 4 sig figs. So let's say you're running a problem and your answer ends up being 400.2 2, 3, 1. And you need to report that as 3 sig figs. Well, if you just say 400, that's only 1 sig fig. And you can't say the 0.2 because that would be 4 sig figs. So there's only 2 ways of doing this. One is using scientific notation. You would say 4.00 times 10 to the second. Or an easier way is just by saying 400 point. So adding the point makes that all those numbers significant. So 3 sig figs down there. Moving on, sig figs operations. So this is really why it's important we use them, because when we make calculations, you need to know what you round off to. The rule is this: for multiplication and division, your final answer is limited to the number of sig figs and the measurement you used with the least number of sig figs. Sounds complicated. Let's do an example. So let's say you're doing some kind of calculation with area, length times width, and let's say your lazy lab partner comes back and says, this distance is 42 centimeters, and your proper precision lab partner comes back and says the other distance is 27.13 centimeters. Let's find the area, length times width. So we're going to multiply these together. 42 times 27.13 gives me 1139.46. And the unit, centimeter times centimeter, centimeters squared. In math class, that would be your correct answer, but here in science, we can't report this. If you report that number, it's almost like you're lying, because this is so precise, and it's kind of based on this kind of crummy precision here. So here's the rule. You look at how many sig figs in each of the numbers in the problem. 2 sig figs, 4 sig figs. Which one is smaller? 2 sig figs, that's what we limit this to. So this number has to now be rounded off to 2 sig figs. So to do this, you have to just kind of, think about it. I don't really like to make up rules for this. You can usually just kind of write the first number down and then kind of round the second one off. But in this case, if I have 1139, I know I need 2 sig figs. I'm going to look at this 3, and since that 3 is less than 5, I should say, it kind of rounds off to zeros. So I would report this as 1100 centimeters squared. 2 sig figs in my number. Okay, so this is proper precision. You might say, well, if we know it's that, why would we make a lazier answer? Well, it's based on this idea that you can't tell me it's this precise if you don't know it based on that. So this is multiplication. Division's the same thing. If you're dividing 2 numbers, look at the number of sig figs, take the one that's smaller, and round your answer off to that. Okay. Example I use really quickly is density. That's mass over volume. Let's say the mass is 2 grams. Well, let's say 2.0. 2.0 grams. Let's say volume is 3.0 milliliters. What's the density? Well, 2 over 3 is 0.666666 repeating. And in math, you could just write 0.6 with a line over it. But you can't do that in science. So you look at the number of sig figs. 2 sig figs, 2 sig figs. 2 is obviously the same here. So 0.6666, that's what your calculator says. We need to round this off. Well, you can't just cut off the 66 and say 0.66, because this 6, being higher than a 5, is going to make this round up to a 7. So 0.67 gram per milliliter. Okay. Moving on to addition and subtraction. Now, please note this. I include this with sig figs, but it actually has nothing to do with sig figs. It has to do with decimal places, and by that I mean numbers after the decimal. Your answer is limited in precision to the measurement you used with the fewest number of decimal places. So let's say you're adding up the sides of something for the perimeter, and your lazy lab partner says it's 2.1 centimeters, and your other 2 lab partners say their side is 4.09 centimeters, and you report yours properly as 6.72 centimeters. You have to add these up. Let's say it's like a triangle, which I'm sure probably doesn't actually work. From the calculator, we're going to add it all up. 2.1, 4.09, 6.72, and that's going to equal 12.91. And when you add centimeters, it's the same unit. So now we need to think, are we going to report this, or do we have to round it off to something? And we're not looking at sig figs. You're not going to say 2 sig figs, 3 and 3, so let's round that off to 2. You look at decimal places. 1 decimal place, 2 decimal places, 2 decimal places, you're limited to the 1. So this we have to round off to the 10th place, so we're just going to knock that 1 off. If that 1 were higher than a 5 or higher than a 4, this would round up to 13.0. So that's the rule for addition and subtraction. Scientific notation. This is number 5. Here I'm just going to kind of introduce the basics. I think most of you have seen this in the past. Scientific notation is a way to write very large or very small numbers in an easier way, especially when you're kind of working with them mathematically. So let's say you have 419 million, or we'll even say billion. Okay? How do we put this in scientific notation? You imagine you have a decimal point at the end, which, by the way, in science, like this is much, much different from this. So just imagine you have a decimal point, and let me see if I can grab it. And then you're going to kind of move this decimal point until the number becomes between 1 and 10, and that's important, 1 and 10. So in this case, I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So I'm moving it 11 times, I now have 4.19. Now since these zeros were never significant, I don't need to write them all out. So 4.19, and then you write times 10 to the 11th, because I moved it 11 times. If you have a really small number, like 0.000000309, let's add the 0. So in this case, we're going to be moving the decimal point to the right to take it between 1 and 10. So I could tell it has to stop here. So 1, 2, 3, 4, 5, 6, 7. So we're going to write 3.090. And this is important. If you looked at the original number of sig figs, none of these are sig figs, but these all count. That extra 0 does count. So you have to write it in here. 3.090 times 10 to the, what is it? 1, 2, 3, 4, 5, 6, 7. 7, but since it's a small number, we write -7. And what 10 to the -7th means is 1 over 10 to the 7th. So basically you multiply that number by 1 over 10 million. So that's scientific notation. Let's do some quick practice taking numbers out of scientific notation. So let's say you have 4.23 times 10 to the 8th. We're just going to kind of swoop that decimal point 8 places to the right. Because it's 10 to the 8th, we know this is going to end up being a really large number with a lot of zeros at the end. So 1, 2, 3, 4, 5, 6, 7, 8. Add our zeros and let's rewrite it cleanly. So 4, 2, 3, 0, 0, 0, 0, 0, 0. And even though we have a point at the end here, we cannot include that. Because if you put a point at the end, all of a sudden you made these all sig figs, and we can't do that. The original number was 4.23. 3 sig figs, so we leave it as just our 3 sig figs. So that's our number. Let's work with a small number. Let's say you have 4.2600 times 10 to the -7th. Okay. In this case, 10 to the -7th means it's going to be a very small number, so we're going to have to add a lot of zeros in front of a decimal place. So let's move our decimal point. 1, 2, 3, 4, 5, 6, 7. I'm running out of space here. Let me redo that just so I can be sure. Starting here, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6 zeros. And in this case, we have to leave these zeros at the end. So let's just rewrite this cleanly. 0.000000. 6 zeros, 42600. You have to include the zeros at the end because this is 5 sig figs, so this needs 5 sig figs. Scientific notation operations. This is when you multiply or divide, or add or subtract. Now, You're going to be able to use calculators in this class, but I think it's important to understand the kind of fundamentals of this so that when you're multiplying two numbers together, in the back of your mind, you should have an idea of what the exponents should look like. Because it's very easy to forget a parenthesis or misplace your parentheses, and you end up getting a completely wrong answer. So if in the back of your mind you know what it should sort of look like, it'll really help you out. Scientific notation for multiplying. Step 1, multiply your front numbers. Step 2, add the exponents. Step 3, adjust if necessary to proper scientific notation. For example, 6.19 times 10 to, then I'll go tricky, I'll make it negative. Negative 9th times 4.10 times 10 to the negative 8th. Okay? So if I were to multiply these together, step 1, multiply your front numbers. 6.19 times 4.10 equals 25.379. Now you can adjust now or at the end. I always like to do sig figs now, at least with one of these types of problems. 3 sig figs, 3 sig figs. We need 3 sig figs. So 25.3, can I knock the 7/9 off? No. The 7 makes this go up to a 4. So 25.4. So that's step 1, multiply front numbers. Step 2, add the exponents. Negative 9 plus negative 8. Same thing as saying negative 9 minus 8. That's going to be negative 17. Tricky with that. So we say times 10 to the negative 17th. Step 3, adjust if necessary to proper scientific notation. Mathematically, this is fine, but it's not proper scientific notation. This number needs to be between 1 and 10. So what we do, I like to say 1 up and 1 down. One of these numbers has to go up, one has to go down. So since this is too large, this is going to go down. We're going to move the decimal point to make it go down, 2.54. So since this side went down, this side has to go up. Tricky again. If you have negative 17, we're going to bring that up. So we're going to make it negative 16. Because negative 16 is larger than negative 17. Okay? So that's what your answer should look like. And when if I were to work this out later in the year with a calculator, if I were to plug these in, I would just be thinking in my head, the number should look something like negative 17. And this is close. And, it would be negative 17 if this weren't, 25.4. Division, it's similar. You divide your front numbers, you subtract your exponents, and then you adjust if necessary. Quick example, let's do 9.3 times 10 to the 7th divided by 4.96 times 10 to the 12th. All right. First step, divide your front numbers, 9.3 divided by 4.96. And that gets me 1.875. Now you can adjust the sig figs now or later. Let's just get it out of the way now. 2 sig figs, 3 sig figs, 2 sig figs is my number. So 1.875 is going to become 1.9. I can't just knock the 7.5 off because that rounds up. Times 10 to the, subtract exponents, 7 minus 12 is negative 5. Adjust if necessary. Well, in this case, we don't need to adjust. 1.9 is between 1 and 10. We're good. Adding or subtracting numbers in scientific notation. Okay. The number one most important rule here, the exponents must be the same. Adjust them until they are. My tip, round the smaller exponent up to the larger one as opposed to the larger one down. You get the same answer, but you have to take an extra step of adjusting it at the end. Add or subtract the front numbers, keep the exponents the same, adjust if necessary. So, let's do this on a separate slide. 6.91 times 10 to the 4th plus 9.07 times 10 to the 5th. So if you want to add these, you can obviously use your calculator, but again, it's important to know the fundamentals. To add these, you can't do anything until the exponents are the same. So we have to adjust. Now, my tip, take the smaller one up, and you'll see why. So if that 4 is going to go up to a 5, what does this have to do? Well, one goes up, one goes down. So this is going to have to come down in size. And I don't mean like take 1 away from that. Since 10 to the 4th going up, you're multiplying it by another 10. We're going to divide this by 10 by swooping the decimal point to the left. 0.691 times 10 to the 5th now, plus 9.07 times 10 to the 5th. And now you can see the exponents are the same. Add the front numbers. We get 9.761. And now this is tricky when we're adding. We look at our decimal places. 2 decimal places, 3 decimal places. I'm limited to 2 decimal places. Cut the 1 off. 9.76 times 10 to the, keep the same number, 5th. Adjust if necessary. We don't have to. All right. Number 7, using graph data to derive a scientific equation. Scientific equation, what we mean by that is taking what we learned in math class, like y equals mx plus b, and putting it in the context of a chemistry lab. We've done this once with our volume data. We'll do it plenty more times. So I made up some fake data. This is probably very small, so I'll kind of enlarge it. But this is going to be volume of a cube measured in ml and centimeters cubed. I plotted liquid volume in milliliters on the y-axis and calculated volume in centimeters cubed on the x-axis. Let me enlarge the kind of box here to see. But you can see it makes a straight line, give or take. All right. So here's what we mean when we say write the scientific equation, or write the line of the graph in chemistry terms. Since this is a straight line, we're going to use the basic formula y equals mx plus b. That's your line of a graph from math class. And this is good in math class, but in chemistry class we want to take the graph and actually apply it using chemistry terms. So what we do now is we look at the graph and we say, all right, instead of saying y, what can we say? And I don't mean randomly choose a value and plug in a number. I mean, like, what is the concept of y in this? Well, my y-axis has liquid volume in milliliters. So we can write volume in milliliters. That's a little more precise than saying just ml. Okay? So volume in milliliters, that's my y. Equals, for my m. For m, you're just going to pull it right from the graph, 0.9727. Okay? You can't include the units. I usually, when I write the equation, I generally don't. Your teacher might want you to, so you might want to check on that. X. Let's see what we can write for x. Do not delete this. Okay? For x, again, you're not just going to choose an x value. You're going to say, well, what does x really mean on this graph? Well, here's my x-axis. You can see it's calculated volume in centimeters cubed. So let's write that in. So volume in milliliters equals 0.9727 times volume in centimeters cubed plus b. Now, before you just write it, this is when we apply our 5% rule. Let's take a look at what I mean by that. B is your y-intercept. It marks the point at which it crosses the line, or crosses the y-axis. Now, sometimes we need to include it, sometimes we don't. The reason you wouldn't include it is because in a lot of cases, the y-intercept is only sort of there because of human error during the lab. In this case, and in several other cases we have coming up, the lines should pass straight through 0, 0. But because, spills happen, measurement errors happen, we get this y-intercept. It doesn't cut perfectly through. But if it's so darn close to cutting right through, we can basically say, just imagine if it, did go right through. So if this y-intercept is less than 5% of the total, we say, you know what, it's so insignificant that it must have been there just because of human error. But if it's more than 5%, you can't really just cut anything more than 5% out. And that's kind of a general rule in science in general. Like a 5%, a 95% confidence rating is kind of an important concept. So if you're less than 5% off, you can remove it. If you're more than 5%, then you have to keep it in. Even if you kind of know in the back of your mind that it shouldn't be there, that it should pass right through, if it's more than 5%, you have to include it. So let's run the actual numbers here. So I'm going to say 5% rule. You take your y-intercept, which is b, you divide it by y max, and you would say times 100%, or just say times 100 and then add percent. And you want to say, is this going to be more or less than 5%? So the rule is, if more than 5%, include the y-intercept. If less, exclude it. Or ignore it, or whatever you want to say. So let's run the numbers. The y-intercept is 17.80. I want to say, is that more or less than 5% of my y total? 17.80 divided by my y max, so the highest y value, and if I give you data, use the data. So this is my milliliters, there's my milliliters, so the highest one is 689. Okay, so when I run that through, it comes out to 0.02583, but to turn that into a percentage, you say times 100, and you can see that comes to 2.58%. Or, let's see, we need 3 6, yeah, that's right, 2.58%. So what this means is we were really close to going right through the middle. We were only off by like 2.58%. And because 2.58 is less, we can exclude this. So my equation of this line for that data that I showed you, that. Volume in milliliters equals 0.9727 times volume in centimeters cubed. That's your answer. I ran a second set of data. Let's do another quick calculation here. Y-intercept is negative 39.42. Now, when we deal with negatives with our 5% rule, we're looking for like the total kind of magnitude of the number. Almost imagine we're looking at like absolute value. So if it's negative, just assume it's positive. We're looking for how far off it is, whether it's off in the positive or off in the negative region. So 39.42. I'm going to ignore the minus here because I just want to say, you know, how far off of 0 was it? Divided by my y max is 621 times 100 gives me 6.347, so I'll call that 6.35%. Now in this case, because it is more than 5%, even though I know in the back of my mind it shouldn't be there, I can't ignore it. I have to include that, just to be honest about my data. So for that case, we're going to say, we'll start with y equals mx plus b. For y, it's volume in milliliters equals, my m on this graph is my slope, 1.001, times volume in centimeters cubed, that's my x, and now I have to include my y-intercept because it failed the 5% rule, minus 39.42. And this is my equation for that second one. So in the first one you didn't include b, in this one you do. Last thing I want to get to is percent error. Now I actually haven't even covered this in my class, so you guys may have in yours, but here is percent error. I mean, before we just put a formula up, let's talk about it. Percent error is how much, how far off you were from ideal. If you're taking a test and your goal is 100% and you only get 80 out of 100 questions, well, you got an 80%, but your percent error would be 20%. You're 20% off of perfect. So here's how we're going to find percent error. We're going to say, take the actual, and by this I mean like the known value, minus the experimental. And by this, I like to say what you got. Let me spell correctly. So this is how far off you were. If you wanted it to be perfect and you were off by a little bit, this is just the difference. However, we're going to take this and put it in absolute value. Again, if it's negative, we just want how far off you were. So put it in absolute value. If it's negative, make it positive. And since it's an absolute value, it doesn't actually matter which one of these you subtract from the other. If you put this over here and that over there, as long as you apply the absolute value, you'll still get the same answer. So that's why I sometimes flip-flop these, because it really doesn't matter. It's the true value minus the experimental value, but you have to divide it by, and this one has to be correct, the actual value, or known value. Okay? So in the case of your test, you wanted 100. Actual, theoretical, perfect value would be 100. You actually got 80. You did okay. So 100 minus 80 gives you 20. 20 divided by your actual value, which would, in that case of the test, is 100%. 20 over 100 is 0.2. To turn that into a percentage, you multiply by 100. And then add a percentage. Okay? So this is your basic formula for percent error. In simple terms, it's how far off you were from the perfect number, divided by what the perfect number should have been, times 100%. Let's do a couple quick calculations involving these. Okay? Now in this sort of data table here, the y and x values are trying to indicate, it's basically, milliliters divided by centimeters cubed. What you probably learned in class is that those are the exact same thing. And it doesn't matter that it's just for water. It's just the same thing in every case. A milliliter is the exact same thing as a centimeter cubed. They're measurements of volume and they equal one another. So because they equal one another, the ratio of milliliters to centimeters cubed should be exactly 1. So the ratio here is your slope. It's this divided by this. It should be 1, and we were close, 0.9727. So let's run a percent error calculation for that. So my actual or known value is 1. And in this case, we could just say 1 sig fig, but it's really like infinite. It's like 1.0000 forever. 1, and in fact, just for precision's sake, let's just add my zeros. Okay? Minus what you actually got, which in this case was 0.9727, divided by what you should have gotten, times 100%. So let's run the numbers. 1 minus 0.9727 equals, divided by 1, which you don't even really have to do. Keep in mind that will not always be 1 though. Times 100% gives me 2.73%. So you're off by, just under 3%. And that makes sense. You wanted it to be 1, but you can see you were just short of it. So your percent error is 2.3%. Let's run the other numbers. This I can already tell right off the bat, that's going to be very close. 1.001. You know what, before we do this, let me go back. I think I noticed a mistake I made. 4 sig figs. 4 sig figs. This we're going to assume is infinite sig figs because it's just the concept of 1. When something is perfectly equal and the concept of 1 is true, we can just call that 1. So, or call it infinite sig figs. So this should have 4 sig figs. So even though it came out just to 2.73, I'm going to add my 0. This is the correct answer. Back to the next one. So we had 1.001 and we had 1. Now, again, it doesn't matter which one you put first, but just to be consistent to myself, let's put what it should have been, which was 1.000 minus 1.001, so that's how far off I was, divided by 1.000. Okay, let's run the numbers. 1 minus 0.001 is 0.999. Sorry, minus 1.001. 1 minus 1.001 is negative 0.01. But since we just put this in absolute value, make it positive. Divided by 1 is the same number. Times 100% is 0.1%. But just to be consistent with sig figs, 4 sig figs, infinite sig figs, because these are like mathematical concepts, 4 sig figs I should report 0.1000% error. So 1/10 of 1% off. Okay? So that is the end of the video. I'll do the next one next week. See you in class.